Okay, so now we're going to look at base conversions. Different numerical systems involve different bases than we've seen with some of the other systems like the Mayan system, and some of the others that it could be base 20, it could be base 60. So we'll learn about a bunch of them, but we'll focus early on with base 12 and base 16. All right, but let me just read this. To represent a number in positional numeral system, I keep doing that, with base B, we need B amount of symbols for digits 0 to B minus 1. All right, the digits used in any base go up to 1 less than the base value. All right, so very simply, so in our decimal system, which is base 10, we go from 0 to 9. All right, 9 being 1 less than 10. All right, so that's the idea there. All right, so binary system, which is base 2, we'd go from 0 to 1 less than 2, which is 1. All right, after you go through 9 digits, if we're doing something like base 12 or base 16 or anything larger than base 10, we need other symbols to represent those values. All right, we're trying to do this with single characters rather than having multiple numbers put next to one another. So we'll see that when we do like a base, hexadecimal, base 16, after we get to 9, so I'll kind of steal my own thunder a little bit here, but we'd start off with 0, then 1, 2, 3, 4, 5, 6, 7, 8, 9. I need to get up, this is base 16, so I need to get up to 15, but I only want to do it with single characters. So instead of saying 10, 11, 12, 13, 14, 15, what I'll do is I'll use A for 10, B for 11, C for 12, D for 13, E for 14, and F for 15. All right. So really you could use any symbols, but this is what anybody who does hexadecimal notation uses. All right. So we kind of conform to that. All right. But yeah, anyway. So in 151, converting from other bases to base 10, to convert a number from any base to base 10, multiply each digit by its corresponding place value. And we've done this before with the ancient systems. So we're just going to kind of like sort of bring it closer to the modern era, I guess. Then add the products together to obtain the equivalent decimal value base 10 number. All right. This process effectively rewrites the given number in terms of powers of 10, and then we get a more familiar looking number as a result. So that's create a base place value table, increasing order. The powers of the base increase the order in order from right to left. Then we fill in our digits, multiply by their place values, and then add the products. All right. So if I'm converting 3012, all right, because I don't want to say 3012, because that would be that's how we think of something as a base 10. All right, but this is in base 4. All right, so going back to my table here, we have binary base 2, quinary or quinary, depending on how you pronounce it, that would be base 5. I want to say it's quaternary for base 4, but I could be wrong about that. Then you have octal, decimal, duodecimal, hexadecimal, and so on. All right. So yeah, what we're doing here is we're lining up our place values: 4 to the 0th, 4 to the 1st, 4 to the 2nd, and 4 to the 3rd. All right. And each one of those corresponds with a number. All right. that's where this table down here comes into play. But really what we would do is kind of what we were doing with the ancient stuff. 3 of those 4 to the thirds plus 0 of the 4 to the seconds plus 1 of the 4 to the first and 2 of those 4 to the 0th powers. All right. Now, whether you do it in your head or on paper, however you want to do it, there will be some multiplication involved. Some of it's not going to be bad because 0 times anything is 0. All right. So this would be 1 times 4, which is 4. 2 times 1, because anything to the 0th power is 1. So 2 times 1 is 2. And we just need 4 to the third, which is 64, times 3. So I think that's 192, but I'll just verify. Yeah, 192. Which, when you add it all together, 198. Now that's going to be 198 in base 10. All right. Now, since we do have a need for this, like 3012, like I said before, I'm not going to say 3012 because that's how we would say it in base 10. That was base 4. Now it's in base 10. I'll put a little subscript of 10 there. However, it's kind of a standard sort of convention that if you don't have a subscript, it's assumed to be base 10, but not everybody goes by that. So you know, you might see it both ways. That's really the moral of the story there. All right. So it's really the same idea. If it's base 5, if it's base 2, whatever it happens to be, you would just multiply by its place value. But the thing is, if you have something that is base 5, for example, you could never have a digit that would be greater than 4. All right. Because again, just going back to my list here, the binary digits go from 0 to 1. The quinary go from 0 to 4. Octal go from 0 to 7. Decimal we already talked about. Duodecimal. So that's going to go up from 0 to 11. All right. Oh, and we can't have more than one character, so we need some other symbolic representation for 10 and 11. I think I made a note of it here somewhere. Yeah, we use T for 10 and E for 11. All right. Like I said, the characters can be kind of whatever you want, but if you want other people to understand what you're writing, then it kind of makes sense to develop some sort of familiar system. All right. But yeah, you'll notice that in the case of base 4, you see those numbers, those digits, 3012, right? If it's base 4, I could only have values between 0 and 3. So I would never have, I mean, it would either be a typo or a trick question or something like that, where I would say, like, for example, convert, let's say 8156 in base 4. All right, that regardless of what I'm telling you to convert it to, that couldn't work. All right, so that would never, it's not possible. All right, but if this were a 10, that would be okay. If it were really anything bigger than, anything that would allow a maximum number of 8 to be part of the set of digits. All right, so a lot of the same stuff there. We get into base 12 and base 16. I have a whole thing on base 2. We'll get to that as we go, because binary systems are foundational in a lot of areas, specifically computer science. So it kind of deserves its own attention. And even hexadecimal has applications in computer science for colors, for example. All right, and we can talk about that as we go forward. But if I want to convert something from base 12 to base 10, I'm looking at, again, the place values. So this is 12 to the 0th, 12 to the 1st, 12 to the 2nd, 12 to the 3rd, and 12 to the 4th. Obviously, for the bigger numerical systems or larger number of bases, or maybe not number of base, it's more like characters in each base. The more complicated the math gets, and more you're likely to incorporate a calculator into your investigations. But like, for example, that T, I would have to know that that's the equivalent of 10, and the E is the equivalent of 11. All right. So this would be the same as saying I have 2 of those 12 to the 4ths plus 10 of those 12 to the 3rds plus 3 of the 12 to the 2nds plus 11 of the 12 to the 1st values, and 8 of the 12 to the 0ths. So that's something I would just chuck into my calculator. And again, whatever calculator you want is fine. I use the NumWorks calculator. It's pretty good in terms of being a good, or the they have handheld versions of these, but the app version, whether it's through a website or if you download an app for your phone or something, it's pretty user friendly. But if you have something that you prefer, I know some people love the TI calculators. You could just type in values into Desmos if you want. I'm just going to put a 1 there. All right, so we're looking at 59,324. And again, if I don't put a subscript after it, I'm saying that that's a base 10 number. It's a decimal number. All right. If you're looking at something that's hexadecimal, all right, so we just did duodecimal, but if I did hexadecimal is base 16. I know that from my little subscript here. All right. For this one, I almost always need the like that little number line that I had before. All right. So I'll just kind of grab that and bring it along. Because it happens even to me where I get crossed up a little bit. And I'm like, wait a minute, is that a 15 or a 16 or what am I looking at here? So I'll have my little number line here. And then sometimes, even just for my own benefit, I'll just put a little key here representing what these values would be numerically. All right. So my C is worth 12. All right. So I'll make a little, like I did before, I'll make a little note below it that's a 12. My F is a 15. And my E is a 14. And again, we use the place values. So 16 to the 0th, 16 to the 1st, 16 to the 2nd, 16 to the 3rd. All right. And this is all up on my screen here, so I can just kind of point to it. For that first calculation, it's 12 of those 16 to the 3rd powers. Then we have 9 of the 16 squares. And we have 15 of the 16 to the 1st power and 14 of those 16 to the 0ths. And we pop that into a calculator and we're good to go. All right. The last one is binary. All right. And you can see the whole setup there, but it's the same idea. The calculation should actually be a little bit easier, or actually a whole lot easier for binary. All right. The place values will get larger, but it's still the same idea. 2 to the 1st, 2 to the 2nd. 2 to the 0, 2 to the 1st, 2 to the 2nd. I wrote it, but I didn't say it. 2 to the 3rd, 2 to the 4th, 2 to the 5th, 2 to the 6th, 2 to the 7th, and 2 to the 8th. And again, it's just kind of going down the line benefit, or benefit's not the right word. It's more like, let's put it this way. Some of these conversions are easier than others. Binary is probably the easiest one because it's made up only of zeros and ones. So if I'm saying I have one of those 2 to the 8ths, but I have 0 of those 2 to the 7th, 0 times 2 to the 7th is 0. So in my calculation, I could essentially disregard anything that's got a 0 attached to it. So I'd have 1 times 2 to the 8th plus 1 times 2 to the 5th plus 1 times 2 to the 3rd plus 1 times 2 to the 2nd plus 1 times 2 to the 1st. Everything else would zero out. All right. Now, 2 to the 8th, you might not know that off the top of your head. All right. But maybe you know 2 to the 5th power, for example, is 32. So 1 times 32. 2 to the 6th is going to be double 32 is 64. 2 to the 8th is 128. So 1 times 128 plus 1 times 32 plus 1 times 8 plus 1 times 4 plus 1 times 2. All right. So 128 plus 32 is going to be, I think, 160 plus another 8. So 168, 172, and 174. Okay, not even close. Where did I screw up? All right. 2 to the 8th, I screwed that up, huh? Oh, look at me. It's 256. Tell you how easy something is, and then I immediately mess it up. I'm going to leave it in the video. Nobody's perfect. Yeah, it was, wait, 2 to the 5th is 32. 2 to the 6th would be 64. 2 to the 7th is 128. 2 to the 8th is 256. All right. Nope. 256. All right, so one of those 256s plus one of those 32s, so we're up to 288. Then add another 8, so 296, 300, 302. 302 answer. There we are. All right, so we get it that way. Now, go ahead and put it in the calculator. I just demonstrated why one might want to do that, so that's not a bad idea. But now you should be good to go to tackle the problems on 151. All right. In the next video, we're gonna go back the other way. All right. So we'll go from base 10 to other bases.